Thank you very much, Professor Noda. Thank you for kind introduction. Perhaps I think you are right. Many people surrounding me used to think I was a totally crazy person. Here, this is the agenda of my lecture today. 13 or 12 years ago, I left Kyoto University. My name is Matsunami, but in the position of the Professor Emeritus. But in a way, ICT innovation is the name titled for 20th century. That's the societal change to the information society, and the semiconductor was critically important. And previous speaker already covered lots of my topic. That means effective utilization of electric energy. So I can be short for this. But in order to do that, currently silicon is the majority to cover that area. But from the energy saving point of view, silicon carbide power semiconductor is very much useful. And Kyoto University, I proudly say, have made a lot of contribution. But those activities in the past was regarded as crazy approach. And I would like to give you the status quo of the silicon carbide power device. And in order to realize the green innovation and the future will be explained in my own way. So, as you know very well, this is the first #1 computer in 1946. Vacuum tubes are used. This is 30 meters in length. It started to operate, and 10 years later, this was outdated. What was the reason for discontinuation? Now, semiconductor had emerged in the world. I will touch upon later, but if we use the semiconductor, then electric energy or signals can be converted in multiple ways, especially between light. PV cells use the light and get the generation of heat, and the other way around is the LED or laser. Then we have other energy or the signals. We can have the interactive conversion, but I will not touch upon this today. In 1947, but published in 1948, transistor was made by galvanium. That was the report from the Bell Lab. And then little by little, silicon increased in its use. Integrated circuit was not so much outstanding. Silicon is just partially used. However, we used to use electric circuit, but it's now the integrated circuit that's a new concept. And in 1970s, now program was added on. That means the combination with the software has been leading to the computer of today. That's the whole flow of the technology. That is the paradigm shift of a society by progress of electronics. Paradigm shift did take place. Please allow me to say so. So compared with the first computation machine, we had this road, desktop PC, tablet today, and especially Japan has been good at making digitalized camera and a mobile phone. All those are combined now. That crystallization has been displayed with the smartphone group. This type of machines were developed. But the contents are not equal. However, fusion of information technology and communication is the symbol, so cloud system can be utilized. Therefore, even with small size, that can do the same work which was done by the large device. So cloud system is the popular word today. But using smartphone, recently I see young people embedded in enjoying games only. In cultural aspects, I have a concern. And a brain scientist said that if people just involved in the smartphone playing the games, and then frontal lobe development of the intelligence will not be developed any further. So therefore, this is the new social issues. Kyoto Prize has the good teaching. Science and technology can give us lots of convenience. However, on the other hand, new issues will be given to us to face in order to keep the civilization level. And now electric and light signal change was started. So the light emitting diode and the laser was further developed in 1954. Bell Laboratory, for the very first time, made the power as a power source for the phone, that is the PV cells, as Professor Artwork said in previous talk. In 1995, gallium nitride is used. So now most of the lighting is using this. Therefore, in the semiconductor world, photonics progress is triggering the paradigm shift. Even today, for the fluorescence lights production in Japan, in 2 years to come, those will be discontinued. So LED will be the representative names for lighting. Now let me move on to the second agenda, that's the effective utilization of the electric energy. Dr. Atwater mentioned the importance of energy. Therefore, I do not need to touch upon this. Energy is very important. And for conversion, that is the major role for the power electronics. But in many cases, this is not visible from outside. Or the diode or PV cells can be visible, but the power electronics are embedded in devices. So we are bolstering from behind. Therefore, from the outer side, it's totally invisible. And the silicon semiconductor is the major role to be played. But recently, silicon carbide, that material of semiconductor, has been emerging, but very, very rapidly. I myself was involved in the research, and I would like to give you the road that our research teams had taken, and commercialization will be mentioned for the purpose of the benefits of the other people. Silicon carbide should be further progressed. What is the evolution that we are making? And especially LED is very popular, but that nitride system could be used for the power, so that potential will be touched upon. Well, this is the common sense for scientists. This is the power electronics, how to convert the direct current and alternate current. As you know, for DC, photovoltaic cells, or what we call battery, has this DC. Along with the time, the same potential. Of course, the lifetime is there, so therefore lifetime is limited number, and then gradually voltage declines. But this is the AC. That means that if we just plug into the concert on the wall, then we can get the electricity. That's the alternate current. And the power electronics is the inverter from DC to AC for conversion, and we have converter from AC to DC. So these two inverter converters are well mixed or combined. In order to produce the inverter and converter, very important element is a diode. That means only one way of current running is facilitated. Rectifying is the feature, and switching is required. Two types of transistor are available. One is the bipolar transistor, NPN, PNP. That means the impurity things are infused to change the structural material. And MOSFET is metal oxide semiconductor field effect transistor. That is the principle of the capacitor to convey the electric signal. And I will touch upon this later. One case example of the inverter circuits are shown here. This is the plug, and then get the AC that will be converted to DC. And that DC electricity has the inverter here. This is the diode, a transistor placed. And we need L or C, but anyway, those are skipped. And then that is running the motor. Conventionally, motor directly attached to the power source. And then motor was rotated. But in recent days, most of the motors are controlled by inverters. For example, if you use the home electric appliances, inverter, refrigerator, inverter, air conditioner, inverter, washing machine, all those are using the inverter. Now, what is the expectation for energy saving and the specific expectation given to power semiconductors, silicon nitride? Well, up until the consumer on the transmission line of electricity, there are lots of conversion, DC to AC or AC to DC or increase of voltage. Those are the steps up until the use. 5 to 10% are lost. And as I said, especially for the consumer home electric machines and industrial motors, those are using the inverter. And we use silicon in majority of the cases. And then 10% of the energy produced are lost. So if 2 kilometers of the air conditioner is running, then the 10% are being lost on the consumer side. So, for example, the nuclear reactor had a 10,000 kilowatt, and then if we use the 1 million, and then 150,000 kilowatts are lost. Huge 15% of the energy loss. So if we can do something better, then we can contribute to the green society or carbon-free society. Electricity is so convenient, so everybody think they can get for free and just plug into the electricity consent. But we should have the renovation or innovative change for the power electronics in order to save energy that was generated. This is the expectation for territory for silicon carbide power devices, but first silicon power. So this is the hertz or frequency on x-axis, and the y-axis is the capacity of the power. In history, bipolar transistor was the first one in power electronics in 1970s. But sorry to use the technical word, but bipolar type has lots of the electricity power. However, it cannot respond to the high speed. Therefore, to higher electricity capacity, for example, the DC transmission, large factories are the major users. In contrast, in information process, most transistors have been used. This is for memory and computer. It made a great development. And planar structure is the feature, so the electricity is flowed on the horizontal direction. But because of the property characteristics, it's speedy. However, it cannot be used for high VA. And smart people thought up with a good idea. So this combination of the both would be realized. And those are the IGBT, which are used in today's converters or inverters. Insulated gate bipolar transistor is the abbreviation. That means the structure is the MOS. However, bipolar is used to get the high electricity currency. So currently we are standing at this stage. So as a material, silicon carbide is coming up. You may ask, what is it? Silicon carbide is in Japanese, tanka keiso, and the silicon had played a major role for any kinds of semiconductor device, logic, so memory, PV cells. But the diamond is the hardest material in the world. So 1-to-1 ratio for the mixture, that's the silicon carbide, silicon wafer. This is the diamond original stone, and then silicon carbide wafer is fabricated in 1-to-1 ratio.
And the reason why there's a high expectation for this material is that here you see the property of the device, of the material of the silicon, comparing silicon and silicon carbide. And as Professor Atwater mentioned, talking about the energy gap, how much photon can be exchanged, and there's a difference by 3 times between the two materials. Mobility is pretty much the same. This mobility is how much the electron moves. And the greatest feature is for the difference of this gap by 3 times. And this is supported by the breakdown field. This is different by 2 digits. This is the key point. And also, this is a power device, and so the heat will be generated when the power flows. And so thermal conductivity would be very important to release the heat. And this is about the same as the conductivity of the metal, the copper. And if we combine the different properties, then for the general purpose inverters, the efficiency can be improved as well as the output, and also it could be downsized, and also this material can be used in high temperature. So there's only a need for simple cooling system with a small heat sink for air cooling. So this is what is so interesting about this material. And MOSFET using the silicon carbide, if MOSFET can be developed, then using this silicon carbide, we can develop an IGBT. But for the higher power capacity, the silicon carbide bipolar device will be needed. So instead of using so many players, we only need these 2 for the power device. So this is the dream that I would like to share from now. So for the first half, I focused on how difficult it was to cover this side, and also I shared what is the current status of this material. This is what I would like to explain. Now, I would like to share the story of a crazy guy. And we started this in Kyoto University. I want to share with you what is the turning point that we experienced and what was so epoch-making of our activity to come up with the power device that we have today. So I'd like to reflect the history. As I said, in 1948, transistor was invented. Unfortunately, it could not be used at a temperature above 60 degrees. The transistor would not operate. And at this point, silicon was not available yet. So in the U.S., there was a need for the high temperature. And there was a strong interest for being able to operate at high temperature. And there's a lady from Germany, silicon carbide will not melt. And at high temperature, there will be vapor created, which will create a high-quality crystal. So at this point, again, I would like to say the silicon was not available yet. And in the U.S., there was a mega project that was developed, and also the Netherlands and Japan also participated in the first international conference, as well as second and the third conference were held. And so for the first conference, we talked, as Professor Water mentioned, Shockley participated in the first conference. And in this report for the conference, Shockley said that we need to be able to control this technology, and that would give us much promise for the future. However, this should take time, is what he said. And so Lilly method created high-quality crystal, but as you see in the right side photograph, the crystal is irregular and only thin film can be developed. So, which means that we could not create a device by this method. So Lilly method was not enough for device. And also, transistor was made available from the latter half of the 70s and for IC. And also, operating temperature could be elevated to 125 degrees. So there was a big progress from 60 degrees to 125 degrees. And so there was much focus or interest in silicon, and silicon carbide was now forgotten. And it's as long as 45 years ago that I was interested in this material. And up to that point, so I was trying to elucidate the physical property of the material, but this was really an indirect attempt, which was quite frustrating. So I felt the limit to this effort. And also, in this silicon carbide had such a good property, but it was not fully used in the semiconductor. So with my naivety as a youth, I was very much motivated for wanting to create an electronic device using silicon carbide. And so, well, we needed to... So for the high, there needs to be exchange between high energy and low energy. So I wanted to do a research on luminescence, and I had strong interest in the blue LED. And also, so I had this curiosity for this property for this silicon carbide, and also for the LED. I tried to combine the two, but now many people quitted to research on the SiC. So it took about a decade to come up with a certain achievement. I introduced a buffer layer for gallium and gallium nitride. Could be developed in a different material substrate. So, and it was about 1980 that we succeeded, and so we were able to use the handmade reactor to develop a reproducibility on a silicon substrate. Silicon carbide was grown. So we succeeded in that. And so then we went on to develop the MOSFET. This is using the silicon substrate and silicon carbide N-type. And on top of that, with the P-type silicon carbide, and with the PN junction is here. But the issue is the silicon and silicon carbide. Between the two, there's about 20% of lattice mismatch of the atom. So this means that one side will be pulled, and so this mismatch was seen between the P and the N. And so for the MOSFET, this part has to be flat, but in just a few volts, there is this leakage of the current. So I felt the limit to this material. So I needed to address this lattice mismatch issue. And actually, 16 years later, Kyoto University and Bell and a 4-inch wafer. They have come up with this 3 CSIC on 4-inch silicon. And so on the silicon carbide substrate, I have, the substrate, we had no substrate available in the market at that point. And so for the abrasive or for the fire brick, there was an industrial material, adjacent crystal. So there's a single crystal shown here. And this part was cut off by hammer, and the reverse side was polished, and silicon carbide was to be developed or grown on this surface. It's not the silicon, so we could elevate the temperature. So we had a reactor that we made, that we used for this research. And so you see the natural surface here. And we put an angle here and attach it to the surface where it's polished. Then, if we observe the surface morphology, it becomes very smooth and shiny. And so we always find this mosaic pattern on the surface. So adjacent crystal, which was an industrial material, the white is silicon and the black is carbon. And there is this repetition forming a zigzag pattern, and it goes back every 6 times. Compared to that, in case of silicon or gallium arsenide, there's only a single direction. So if we put it on off the substrate and on the substrate, we did a comparison, and just observing the surface or looking at the R heat, we can see that the stacking sequence is repeated on the off substrate, but for the on substrate side, there will be symmetry created. So we developed a model for this concept, and for the on axis, the terrace is very wide. So when the terrace is large, then when the silicon molecule comes, and if the terrace is big, then there is a choice, pulling the zig or the zag, and they will grow horizontally and collide. Then it would create a mosaic pattern that we saw a while ago. And in case of off-axis, the structure will be a step structure. And so the terrace is small. So for the horizontal side and the vertical side, there will be the chemical link or binding. So there will be a replication. So, and this is actually well known in the crystal growth field, but we are in the device field. So, I thought that we could be convincing with this concept, but this was, and so we created a diode, and so the PN junction. So I said that the reverse flow would be created in a single volt, but here we reached 100 volts, and the crystal was very smooth. This is the model, schematic of the model on the middle, and on the right side. So this is the angle. What is the angle for the, and we call this a breakthrough. But if we think of the early history, then it took a little over 20 years, but we entered a completely new, different phase. And this is, I think, was the turning point of the higher interest to silicon carbide. So there are many devices made globally, but for the crystal, this off-angle technology is widely being used. And in 1993, so there was this very high-quality crystal, and Schottky diode was made, and this was announced in 1995. And what I want to say that, so in case of silicon, the flow is generated from 200 volts. And 1.75 kilovolt, it has this withholding voltage. But so there is a difference of 1 digit in the breakdown field. And so this side would generate heat. So it will be a heater rather than the power device. So power device members, comparing with the silicon, said this is so much difference with the silicon. And so this was quite an interesting aspect. So, well, fortunately, but or not, Infineon has commercialized it in 2001. For me, I would be happy if this technology is anywhere, and that was epoch-making one. And so I was able to demonstrate the technology in a device. And next for the MOSFET. So there's a breakdown voltage on the horizontal axis and specific on resistance on the vertical side, which shows the loss. And so with increased voltage, unipolar device has high resistance. That's the limit for the silicon. In case of silicon carbide, as I said, there's about 2.5 times. And we have MOSFET. MOSFET, well, ended up in a miserable result. And finally, we were able to exceed the limit of the silicon, but we could not make further progress. So as a university, in the future, there's a trench type, and there's a gate here. And if we could create a gate at this side, then in the limited space, we could align many power devices, so the currency could be increased. So since this is the way to go for the future, the university, well, so in a different side, 90 degrees difference, we should look at the property on the planar. And so there was about 20 times, this was to be an improvement by 20 times of the performance. This is what we announced. And for the MOSFET today, trench MOS as well, Japan is now being able to mass produce the device. And Japan has a strength in MOSFET due to this background, and that's why I call this second epoch-making event.
So the world has started to change. Now in device, on top of the 4-inch wafer, device is being produced. Now with the strong request 6-inch, that's 150 millimeter diameter, is tried. That is 150 millimeter 6-inch and a 4-inch. Different from the silicon, it's not dissolved, so sublimation method is used. So the seed would be grown. That's the method for the silicon carbide. Therefore, crystallization properties are quite different from the silicon. This is the Schottky diode. In 95, in 93, data was available, and based on that, 2001, Infineon company commercialized. 9 years later, in Japan, in Kyoto, Rome is the e-component company. Eco Diode made announcement for the possibility of the mass production, and Rome started to send samples to all over the world. And also in December in this year, most transistor will also announced the possibility, and they succeeded in the mass production delivery. As you can see, no leak at all in strange manner. And at the silicon 200 degrees, that is at the lower temperature, okay, but 200 degree, silicon is not working at all. However, silicon carbide has enough margin, even with the high temperature. Now, in order to have this material in the society, a lot of companies or industries should participate in producing the devices. And that was the government decision. And then the government made a lot of funding program. The first triggering research was that in our western part of Japan, several companies or producers had the project for the most updated power device. So all people got familiar with the power silicon carbide, and then nationwide level of the project has launched, and several manufacturers participated in. I think Japan was able to catch up with the level of the world, and then smaller scale of the project followed 6 years ago. There was a request from the government to read the future, and then what we call first projects was launched in the then government. 30 research teams received in total 270 billion yen of the budget. So the big initiative was launched from the then government of Japan. And our field was one of it. And 525 teams made application. Out of those, only 31 that subsidies. We were one of them, and we are proud that we have generated a good data. After that, since last year, SIP program is running since last year. Now, what are the applications? I would like to share with you. This is the reduction of the power loss. Now, first, that was mounted on the Ginza subway. 38.6% of the reduction of the power loss was realized for one train of the subway in Tokyo. That was the silicon switching, and the silicon carbide Schottky diode was used. Now, Odakyu train, that's the train of this private train in the suburbs of Tokyo, then all silicon carbide inverter was mounted on the train, and the total train-wide power loss was reduced as much as 40%. Now, for the high-speed elevator, then the loss of the power was reduced by 65%, especially the volume of the elevator or the installation area was able to be reduced by as much as 40%. That announcement was made 2 years ago. And then that will be developed into the next generation of the elevators from Mitsubishi. Now, the photovoltaic power generation was the major theme of the previous lecture. But power conditioner required, now made of silicon today. But all silicon carbide power conditioner is being developed. That has 97.3% or 98% of the output efficiency. Photovoltaic power conditioners are now possible, and gradually those are used in the actual products. And in Japan, hybrid automobiles, Prius. This Prius was the test car for the tech course only. All silicon carbide inverter was mounted, and then fuel efficiency increased by 5% all of a sudden. I talked with those people, 5%, and are you so happy with only 5%? Because in silicon development, just 0.5% incremental increase is the total amazing surprise. But 5%, that's the one-digit difference. So all Toyota people or vehicle people got amazed to see the silicon carbide. So that was the figure in the test course. Therefore, in January this year, in public road, Camry was used on the public road test. And in Toyota City, fuel cell buses are running in the streets. And then Schottky diode are used for the Toyota, or those are being discussed seriously. And last month, on the 25th, surprising announcement was made that the JR Tokai has the bullet train. For bullet train, experimental train are running. In order to mount a silicon carbide device, what is necessary? So transformers or converter, inverter, power conditioner, or motors, all those are changed. Then with the driving system alone, 10 tonnage of weight was reduced. So if this will be verified, and then this is the essential element to be used, because if the train is getting lighter, then higher speed is possible. I touched upon the home electric appliance at first. If that is the 1 kilowatt of the consumption, the 100 kilowatt is just a waste. Again, for this, if that is the 2 kilowatt, just a 200 watt is just thrown away. So if we can have that conversion loss, and then just in the field of the home electric appliances, as much as 18 billion kilowatts could be saved. So if we can replace the silicon with the silicon carbide power module, then that will be enormous energy saving. However, silicon is dominant and cost is the issue. So user should make a decision whether the efficiency or the price or cheap price. So wafer is getting larger for silicon. Instead of the sublimation, that is the melt silicon, and then seed crystals is given and then rotated and pulled up. That is the Czochralski method to make this large size. Recently, the largest one is 450 millimeter. I don't know who will make device, but the 300 millimeter has been used quite popularly. And now IGBT took 30 years in its evolution, and in those years we had the generation changes and the size was reduced enormous way. So on the silicon side, the progress was made, perhaps because of the silicon carbide push. Now nitride side, gallium nitride property is quite closer to silicon carbide, but the velocity is higher than silicon carbide. So with the high range of the frequency, it can be used. So for general purpose inverter, gallium nitride can have the same performance. However, now high frequency is the target.
But we don't have the substrate available yet, and so we're just using silicon, and heteroepitaxy has to be used. And there is again 20% mismatch, but it says transition layer. By using this layer, we have a gallium nitride and aluminum gallium nitride with this structure. Well, the atom can move in this direction. We can make it available in this structure. So, which means that we can use it in high frequency. And in Japan, for the first time, it was Yaskawa Electric that using gallium nitride, they came up with a power controller, and this power controller are all for domestic PV use. And so I don't know if this is actually made by gallium nitride, but so if we want to operate an electronic equipment, we need a power source, power switch, and power supply. And if we move it 100 megahertz, we can miniaturize the size, and this is what the American venture company is saying. And if I don't know if the gallium nitride is being used or not, but with gallium nitride, yes, it can be used at 100 megahertz. Now, talking about the future, silicon has history of 30 years as a power device. So, for the voltage and the current, it occupies a large portion, but the silicon carbide is now being promoted to be used for above 600 volts. But for gallium nitride, if we fit it in this diagram, this is the territory, this is the area that gallium nitride will occupy. So if we have the vertical type equipment, then it may be a different story. Now, moving on to green innovation, I want to share the achievement of the first project. So this is looking at the power device for silicon carbide against the voltage rating. Currently, silicon. diode can only be used at this range, and if you spend a lot of money, you can go up to more than 1 volt. But then you have for the silicon carbide Schottky barrier diode can cover the pin diode for silicon in terms of the cost as well. For MOSFET and JFET, as I said, will most likely replace the IGBT. It's just an issue of price. But the challenge now is to use the silicon carbide for higher voltage. And so we have applied for the first program. And if for the ultra-high voltage application, we can cover the power transmission and also the DC power transmission and advanced traction. And the bullet train is using 25,000 voltage, so we need a high voltage for the advanced traction. And so in Japan, the power is transmitted at 6,600 volts. And so now in DC, so the target would be to create a device at 13 kilovolts. And if this is achieved, then we need 4 GTO for silicon. But in case of silicon carbide, we can replace it with only 1 unit. So if there are 4 units, then there is high possibility of breakdown. So from 2009 to 2013, our project was adopted in first. And so our target was to come up with a fast and thick silicon carbide epitaxy and defect reduction. So Dr. Kimoto of Kyoto University and Dr. Okumoto of the National Institute of Advanced Industrial Science and Technology and others have participated. And for the P diode, 40 ampere for 5.2 volts, and for Kyoto University has done research on its own, and we have recorded 26.9 kilovolts withstanding voltage, and this is for a device right before IGBT, and we have exceeded 23 kilovolts. So this was a surprise and encouraging that we could make this achievement in the university. And also IGBT that the ICE has worked on, 30 ampere. They have achieved the target, and we need to benchmark ourselves globally. This is the global benchmark. The red shows, well, there's only one company called Cree in the U.S. That has made this high achievement. And in Japan, we are only inferior in 2 aspects. And for IGBT performance, the U.S. has achieved 22 kilovolts, and in Japan it's only 16 kilovolts. So in terms of crystal growth and defect reduction and physical control, Japan has made a high achievement, and also a high level of creating a device of high withstanding voltage. But within the SIP program, we have to find a way to commercialize it. And so this is a request that we are making to the industrial circles. Now, so I talked about the silicon carbide, the expectation we have, and also my experience as a crazy guy of doing research in Kyoto University. And we have reached thus far. And for commercialization, well, we needed support from the national government. This is what I truly felt. And also in the cutting-edge technology development, well, we can be proud of our achievement that we have reached a high level. And for the SiC power device, for the unipolar device has reached the commercial level. And so we are seeing the reduction of the power loss in actual application. And discrete device is what we call in Japan. It's just for MOS-FET for switching. And silicon carbide SPD is now available. So there are wide application. Many 10 tests are being conducted, especially in Europe. There's a high demand for using the railway, but there's in Europe, for diode, there's a supplier, but there's no one company that can cover both areas. So, and for bipolar device is still at the R&D stage, and in order to commercialize it, we need to implement it or integrate it into the various equipments, and so there's an importance for the power electronics applied circuits as well. Now, talking about our challenges about the future, this is the venture company in Kyoto, and this is a dream that we have of using the silicon carbide that only can be achieved by this material, and the vacuum tube switching is to be replaced by the MOSFET using silicon carbide, and this can be applied as the neutron source of the accelerator for the X-ray system for medical use, and or the particle beam treatment for the medical use. If we can use this material for this application, then LINAC will require 1.6 kilometers as a distance, but using this technology, we can just achieve this at only 6 meters, just by the calculation ratio. This is the achievement that we can expect. And also for JR Tokai, as already been announced, for maglev, 12 years later, there will be a bullet train using the maglev, and so this will be using the magnetic force, and there will be require a large electric power equipment, and there will be a need for mega substation in Yamanashi. There's an experimental line that requires 2 substations. And if there's going to be a maglev between Tokyo and Nagoya, the distance will be 200 kilometers, 4 times distance, which means, well, if we consider the power that is needed and the loss at the substation, well, my colleague has been working on the basic research at the Japan Railway, and so was very motivated to use the SiC for this technology, and he's sending me cheers for that to be realized. So thank you very much. That's all from my side. And I would like to express my gratitude to Dr. Kimoto for providing me with a lot of information. Thank you very much.